Okay guys, go ahead and get out your vocabulary notebooks and open to the first clean page in the science section. And then go ahead and get out your science books and open to page 482. Page 482. We are moving on to, we took our test the other day and I'm sure you guys did awesome. So now we are moving on to chapter 11, which is all about forces. So we're on page 482, that's the first page of chapter 11, lesson 1. And the title of our notes today is chapter 11, lesson 1. Right? So before we begin reading, let's go ahead and look at page 482 and listen while I read the look and wonder. Do you enjoy running? When you run, you move very fast and use lots of energy. How can you tell how fast a runner is moving? What affects her speed? So I want you to think about the answers to those questions. I'm not going to answer them now because throughout the lesson, those questions will be answered. So go ahead and turn to page 484. And then read along as I read out loud. Now I will be pausing, just like before. I will be pausing some places and giving out extra information. We will be doing the quick check questions throughout this lesson. Remember the quick check answers are. The quick check questions are the ones where I ask the question, you pause the video, write the answer in your notebook, and then you play it to see if you are correct. So let's go ahead and start with the main idea. The main idea of this lesson is motion occurs when an object changes position. Many forces act on motion. Now we know motion is a synonym for movement. So motion is the scientific term for movement. When an object changes position, either on its own, like us, or animals, or living things, or because something else has moved it, that is motion. So let's go ahead and read. What is motion? When a marble rolls down a tube, it changes its location. Its starting place is at the top of the tube. Its ending place is at the bottom. An object is in motion if its location is constantly changing. So, my cell phone is just sitting right here. As long as it is just sitting right here, it is not in motion. But if I pick it up and start moving it around, now it's constantly changing position, so it's in motion. But then as soon as I set it back down, it's not in motion anymore. Let's keep reading. Position. How can you tell if something is in motion? You look at its position. Position is the location of an object. We're going to add that as a vocabulary word. So, number 1 is the word position, and it is the location of an object. So right now, the position of my cell phone is on my podium, facing up, and it is still. You know something has moved when its position has changed. So, as long as I look at my cell phone, and it is right here on this podium where I put it, it has not moved. Its position has not changed. Words such as left and right, above and below, and east and west give clues about position. When we describe an object's position, we compare it to surrounding objects. So if you notice, when I said the position of my cell phone, I said on the podium. I could have also added under my textbook, and that's another way to say position. I'm telling you where it is in location to both the podium and my textbook. It is on top of the podium, underneath the textbook. The objects used for comparing are called the frame of reference. So that means, in the case of my cell phone, the podium and this textbook are the frame of reference. Another way to talk about position is to describe distance. Distance means how far apart 2 points or places are. Let's add that as a word. we have distance. And distance is how far apart, my brain is getting ahead of my hand. How far apart 2 points or places are. We know that. We know if we're trying to say the distance from here to Nashville, we're saying how far apart Memphis and Nashville are. We can give distance as a measurement. For instance, New York City is about 370 kilometers or 230 miles from Washington, D.C. We can add that New York is north and east of Washington, D.C. So when you're saying distance, you're saying how far apart. Usually you're giving a measurement. Now position would be that northeast. So the position of New York City is north and east of Washington, D.C. Its distance is about 370 kilometers or 230 miles. So those are two different ways to say position and distance. Let's look at this picture down at the bottom of page 444. It says, a horse is a fast runner, but a cheetah is faster. What are their speeds? Oh, that's what we're going to talk about next. So let's pause. Let's not talk about that picture yet. Let's read the next part before we get there. So speed on page 485. All moving objects have speed. Speed is a change in distance over time. So our third word is speed. And speed is a change in distance over time. So speed is how long does it take for that object to move from one place to another. A cheetah can run at nearly 112 kilometers per hour, or 70 miles an hour. You can write these values as 112 km/hr, and that means kilometers per hour, and 70 mph. Now you've probably seen that a lot as you're driving. You see a sign that says speed limit, like 40 mph. That means miles per hour. So your speed is how long it's taking you to cover a distance. So that what miles per hour means is that your speed limit, whatever speed your car is going, if the speed limit is 40 miles per hour, that means it should take you 1 hour to drive 40 miles. If it takes you longer than 1 hour to go 40 miles, you're driving under the speed limit. If it takes you less time to go 40 miles, if it takes you less time than an hour to go 40 miles, you're driving over the speed limit. The speed of a racing horse might reach 76 kilometers per hour or 47.5 miles per hour. So that means it takes an hour for that horse to go 47.5 miles or 76 kilometers. Now let's look at the diagram on the bottom of page 484. We have all different types of animals and how fast they go. We see that this mouse all the way to the left is pretty close to 0. Now that doesn't mean that it goes 0 miles per hour, because that would mean it never moves. But it probably goes like 1, 2, maybe less miles per hour. An elephant is around 20 miles per hour. So that means an elephant can travel about 20 miles per hour. That means if an elephant is walking for 1 full hour in one direction, it would probably go about 20 miles. A horse can go about 40 to 45 miles per hour. We just talked about that. What that means is that it's going to take about an hour for a horse to travel about 45 miles. And then we have a cheetah, which is around the 70 mile per hour marker. So that means if a cheetah just runs straight for an hour, it would get about 70 miles away by the end of that hour. So let's go back to read. How can you find the speed of an object? First, find out how far that object moved. Next, find out how long it took to go to that distance. So what you're doing first is you're finding out how far. You're measuring how far the object went. Then you're going to time how long it took to get there. Then divide the distance traveled by the time spent moving. So if we are taking a cheetah and it went, so first we measured how far it went, which was 140 miles. And then we said it took, and then next we figure out how much time it took. It took 2 hours. So to figure out its speed, we are going to divide this distance by the time it spent moving. So we're going to take that distance of 140 miles per hour, and we're going to divide it by the amount of time it took, so by 2. So that means 2 can't go into 1, so we move 1 over. 2 can go into 14 7 times. 7 times 2 is 14. 14 minus 14 is 0. Bring down that 0. 2 goes into 0. 0 times. 0 times 2 is 0. 0 minus 0 is 0. So that means that cheetah went 70 miles per hour. And that's how we would figure that out. So suppose that in 1 hour you pedal your bike 12 kilometers or 7.5 miles. That means your speed is 12 kilometers per hour or 7.5 miles per hour. Let's keep reading. Velocity. People sometimes confuse velocity with speed. Speed tells you how fast an object is moving. We know that. We know if we are measuring our speed while we're running or driving or whatever, we're measuring how fast we were moving. Velocity describes the object's speed and direction of motion. So that's our next word. Number 4 is velocity. And what it does is it describes an object's speed. Make sure you have that apostrophe because you're saying the object has a speed. The object's speed and direction of motion. So, speed and velocity are not the same. They are 2 different things. Velocity includes speed, but it also tells the direction that something is moving. So a bike racer's speed may be 50 kilometers per hour or 31 miles per hour. If she goes 50 kilometers per hour to the west, however, that is her velocity. So just that number, that 50 kilometers per hour, that's the speed. But if you add in 50 kilometers per hour to the west, that is the velocity. A pendulum is a mass on the end of a rod. So a pendulum is like something heavy at the end of a rod. After its initial push, so that means the first time you push it, the pendulum swings back and forth. It changes velocity on each swing because it's moving to the right, a certain speed, that's one velocity, and then it changes because then it starts moving to the left. Now it may be the same speed, but because it's moving from the right and then to the left, that means there's 2 different velocities. Now look at that diagram on page at the top of page 485. We have a clock. And at the bottom we have a pendulum. So think of like a grandfather clock or something like that. It has that thing that swings back and forth. On each swing, the pendulum of a clock changes direction. That means its velocity changes too. Now its speed may stay exactly the same because it's going the same, it's taking the same amount of time to go the same amount of space. But because it's moving in a different direction, it's moving from left to right, each time it changes direction, that velocity changes because the direction that it's moving changes. Now let's look at this train on the bottom. If this train's speed is 300 kilometers per hour, its velocity is 300 kilometers per hour to the east. So I hope everybody understands the difference. Speed is just how long does it take to travel a certain distance. Velocity is how long it takes to travel a certain distance in a specific direction. So the difference is speed has nothing to do with direction. Velocity has to do with speed and direction. Now let's do these quick check problems. So that means you are going to listen to the question, pause, answer it in your notebook underneath number 4, play the video, listen for the answer, and correct your answer if you need to. Then you're going to listen to the next question, pause the video, write the answer underneath the infer question, play it, check your answer. Okay, and I'll give you hints as we go. So the first one, infer. An athlete running west crosses the finish line of a race. How can you tell that she has moved? Pause this video, write the answer underneath your number 4, and then play it to check your answer. Okay, so the way that we can tell that the athlete has moved is that the athlete moved from the east side of the line, because remember she's running west, so she's on the east side of that starting and finish line, and then she's moving to the west side of the line. That's how you can tell that she has moved. Here's a line right in front of me. So she's moved from where I am with the line in front of her to the west. Now the line is behind her. That's how you can tell that she has moved. So we're using that line as a frame of reference. Remember that from that first part? Now the critical thinking question. A girl runs 50 miles north. Then, I'm sorry, not miles. Whoops, that she would probably not be doing too well after that. Sorry. A girl runs 50 meters north. Then she runs 50 meters west. Her speed does not change. Does her velocity change? Explain. So pause this video, write your answer right underneath your answer from a minute ago, and then play and check. So yes, her velocity does change because she's changing direction. So even though her speed stays exactly the same, her velocity changed because first she was running north, and then she changed directions to run west. Okay, go ahead and turn the page, and let's start reading on page 486. How do forces change motion? How many times each day do you push or pull something to make it move? When you throw a ball, your muscles push on the ball. The ball moves away from you. Each push or pull is a force. So our next word, number 5, which you're writing underneath the answers to those quick check questions, is force. And what force is a push or a pull that moves an object. So force is a push or a pull that moves an object. So if you have a ball and you push it away from you, that would be a force. Now say you have a rope and you pull it towards you. That is also force. Force is just a push or a pull on an object. Forces can be big or small. The force a crane uses to lift a truck is huge, because imagine that crane has to pull really, really hard on that truck because that truck is really heavy. So it has to pull really hard. Think of if you're playing tug of war. If there's like 5 people on the other side, you're pulling really, really, really hard to get that rope towards you. But the force your hand uses to lift a feather is tiny because it's very light. You don't have to lift very hard or pull very hard on that feather to lift it. It's the same as if you have a rope and nobody's pulling on the other end. It's very easy to just pull that rope towards you. Forces can cause objects to start or stop moving. So if you push a ball away from you, it's going to start moving. But say somebody is across from you and they have their hands, hold their hands there, and then the ball stops on their hand. Well, technically they're pushing it, but what's happening is they're stopping it because they're not pushing it away. They just have enough force to make that ball stop right there. Forces can also change the speed or direction of a moving object. So think of playing soccer, and somebody kicks the ball, and then somebody over here on the other team then gets in the way of that ball, stops it, and then kicks it in the opposite direction. That is another way. Forces can change, can cause objects to start or stop moving. It can also change the speed or direction of a moving object. Acceleration. As speed skaters race around a track, they go faster and slower. They turn left or right or skate in a circle. Any change over time in the speed or direction of a moving object is called acceleration. So as an object is moving, if it changes speed, like these skaters, now they're not going to go the same speed the whole time, otherwise it could cause them to slip or fall or run into somebody or anything like that. So as they're moving and the speed changes, that is an acceleration. So if you look down at the diagram on the bottom of page 486, we see some speed skaters. And what they're doing is they are accelerating. So look at the question. It says, how are these skaters accelerating? Well, it shows that orange arrow. That orange arrow is not actually there. That's just showing their acceleration. As they are moving around this corner, they are changing direction, and therefore they are probably also changing speed. So that shows that they are accelerating. The arrow shows that they are turning. And remember, a change in a change in direction over time is acceleration. Let's see. Yeah, let's go on to inertia. Oh, and you will see that this diagram again, so make sure that you were listening. If you need to go back and listen to what I just said, go ahead. I'll repeat it. You can see that arrow shows that they're changing direction. They're turning around this little marker. That probably shows a corner. They need to turn. As they're turning, their direction and their speed is changing. Because think about when you're in a car. If your parents are driving, they're going to slow down as they turn so that the car doesn't tip over. Well, it's the same with speed skaters. They have to slow down just a little bit as they turn in order to not fall over or slip. Let's go back and read. Inertia. A skater will not start to move unless a force acts on her. Once moving, she cannot change her speed or direction unless a force acts on her. Inertia is the tendency of an object in motion to stay in motion, or an object at rest to stay at rest. So inertia. If I have a ball and nobody's touching it, then that inertia is saying that object at rest is going to stay at rest. Nobody's touching it, nothing's moving it, there's no breeze or wind or anything like that blowing on it. It's just still. Inertia says that that ball, without anybody touching it, is going to stay at rest. It's not going to move. Now, inertia also tells us that if we have a ball and we push it, inertia says it's going to keep going unless something stops it. Now, that could be that it ran out of energy, which we'll talk about later, but something still stopped it. Oh, I just realized I forgot 2 vocabulary words. I'm sorry. So let's go back to acceleration really quick. Number 6. And then after this, I'm going to have to erase. Oh, well. Number 6 is acceleration. Which is any change over time. So any change over time in the speed or direction of a moving object. So that's like those skaters. As they turn the corner, their direction changes and they slow down just a little bit so they don't fall over. And inertia. Is the tendency of an object in motion to stay in motion, or an object at rest to stay at rest. So that means that ball, is it just sitting there on the field with nobody touching it and really no wind or breeze or anything like that? That inertia says it's going to stay at rest unless somebody kicks it or throws it. Then inertia says that that object will stay in motion until someone or something stops it. So inertia means if something's moving, it's not going to stop until someone or something stops it. If it's at rest, it's not going to do anything. It's going to sit there until someone or something does something to move it. Okay, the next type of force is friction. All objects with mass have inertia. Remember, inertia is the tendency to stay at rest or to stay in motion. What is it then that brings a rolling marble to a stop? So you might have noticed if you roll a marble across a table, well, inertia would say that it should keep moving forever. And it should keep going and going and going. If we rolled it on a street, it should keep going and going and going. But it stops. Why doesn't it keep rolling with the same velocity forever? The answer is that other forces stop it. So remember, forces aren't necessarily a human or an object stopping it, like getting in the way. Friction is a force that works against motion. Friction acts between the surfaces of objects that touch. So we can't really see it, but it's there. So it's between the surface of that marble and the carpet or the road or whatever it's rolling across. The surfaces rub against each other, slowing the object or stopping it completely. So as that marble is rolling across the ground, the friction between the marble and the ground is slowing it down little by little by little until it completely stops. There's no more, that friction makes it stop altogether. So, let's see, this is number 8, and we have friction, which is a force that works against motion by slowing an object down until it stops completely. So friction happens between the surface of that object and the surface of whatever it is moving across. There is friction between a rolling marble and the surface on which it is rolling. So whatever, whether it's the carpet, whether it's the road, whether it's a bowling alley, whatever. But different types of objects have cause different amounts of friction. That friction causes the marble to eventually stop moving. Not right away, unless it's some things like carpet may have more friction than a bowling alley. The purpose of a bowling alley is for something to roll across. So if you're rolling a marble across carpet, it's going to stop a little sooner than it would if you're rolling it down a bowling alley. There's not as much friction between the surface of a bowling alley and a marble, because they're both smooth, as there are between a carpet, which is a little more rough and soft, and a marble. There's very little friction between ice and the steel blades of ice skates. That's why they're able to move so quickly. But if you take those same ice skates and you try to go down the sidewalk, you're not going to move very well because there is a ton of friction between the blades of ice skates and like the sidewalk, the concrete sidewalk. Oh, let's look at the this diagram at the top. This actually goes more with inertia with this table tennis or ping pong. And it says a table tennis ball changes its motion when a force acts on it. So that's inertia. As it moves, like so one person hits that ping pong ball across the table. Inertia says that ping pong ball is going to keep moving and moving and moving until another force acts on it. Well, in this case, in this picture, the other force is the other player hitting it or pushing on it with the paddle. If it was just rolling across this table tennis this table tennis or this ping pong table, what would stop it would either be the net being in the way, or if you took the net off, the friction between the table and the ball might stop it, or what might stop it is just it falling off of the table, off of the ping pong table, hitting the floor, and then the friction between the ball and the floor would eventually stop it. So now let's do the quick check. So remember, I'll ask the question, you write the answer down in your notebook, play the video, check your answer, and do the same with the second one. So infer. If there were no friction, would a moving object stop moving? Explain. Okay, so the answer is no. If there was no friction and nothing in the way, the object would never stop moving because there would be no force acting against the inertia. So if there were no friction and you rolled something across a surface that had no barriers, nothing in the way, that would stay forever. That would keep moving forever because inertia says that objects in motion would stay in motion unless there is a force, like friction or something in the way, to slow it down. Now the critical thinking question. You are riding in a car. The driver brakes suddenly. What happens to you and why? Okay, so what happens is that when a driver brakes suddenly, like they're driving along and then something, the car in front of them all of a sudden slams on their brakes, so the person driving the car you're in slams on their brakes. What happens is that you experience a forward motion. You kind of get pushed forward due to inertia. The brakes on the car provide the friction to slow and stop the car. That's what those brakes do. They actually push against something to stop those wheels from moving. That friction stops it from happening. But we don't have friction because we don't have anything stopping us, and it's just the air, and the air has very, very, very little friction. So that means we don't stop. But because of our seatbelts that we should be wearing, that stops us from continuing to move forward. If you don't wear your seatbelt, what's going to stop you from continuing to move forward is either the seat or the front of the car that's right in front of you. And if you go through the glass, if you are in a certain position and you go through the glass, you're heavier than the glass, so it's going to push you right through. And that's why it's always so important to wear your seatbelt. Okay, go ahead and turn the page. And now we're going to talk about gravity. What is gravity? A force is acting on you right now. This force acts on you all the time. It is pulling you and Earth together. Hint. We talked about this in the last lesson, or the last chapter. Do you know the name of this force? It is gravity. Gravity is a force that acts over a distance and pulls all objects together. So, number 9 is gravity. And it is a force that acts over a distance. And what that part of the definition means is that it doesn't have to be right there. Like friction stops an object or slows an object because it's right there. They're right next to each other touching. Gravity acts over a distance. So we're not like right there with whatever's causing that gravity. But so it's a force that acts over a distance and pulls all objects together. The pull of gravity depends on 2 things. One is the amount of matter in the object. So is the object heavy? Is it light? Does it have a lot of matter in it? Does it have very little matter in it? And the other is the distance between objects. So how far is this object from where the gravity is coming from, like the moon and the earth? Objects with more mass have a stronger pull. For instance, the mass of Earth is huge. Its gravity pulls strongly on all other objects, keeping your feet on the ground. So because Earth is so huge, there is a lot of that gravity, or the gravity is pulling very, very strongly on everything nearby, like us, where our feet are right on the Earth. The moon is less massive than Earth, so its pull is weaker. Now, because the moon is close enough to Earth, that's what keeps the moon orbiting Earth. Earth's gravity, Earth is so huge that it's even pulling the moon towards it. But it's far enough away that it's not right there. However, the moon is also pretty large, so it has its own gravity pull, but it's not as large, so the gravity isn't pulling as strongly. That's why if you see pictures of a moonwalk, it looks like the astronauts are kind of jumping or bouncing around. Gravity is also stronger when objects are closer together. As the objects move apart, the pull of gravity is less, and that's what I was talking about the moon. They're further apart, so Earth's gravity isn't pulling the moon directly to the Earth because it's not as strong. It's strong enough to hold the moon in orbit around us, but not strong enough to pull it all the way to us so that they like crash into each other. Let's look at this diagram to the left on page 488. Make sure you pay close attention because you might see it again. The question says, how does gravity affect the motion of an apple falling from a tree? So let's look at it. We see this apple falling from the tree. We can tell that because we see where it's moving by that blurriness. It's moving over time. And it wants to know, how does gravity affect that motion? Well, what happens is if you've ever seen something fall from a tree, like a leaf or especially a larger object like an apple, gravity pulls that apple once it's disconnected itself from the tree, however that happens, gravity of the Earth pulls that apple towards it and it accelerates the apple. That means it falls faster and faster and faster until it hits the ground. And then that ground is the force that stops it from moving. So that's the same. That's why something larger like an apple falls a lot faster because there's a lot more mass in that apple than in a leaf. If we see a leaf falling, it just kind of floats down. That's because there's really not that much mass. So gravity doesn't pull on it as strongly. But an apple has a lot more mass, so it pulls on it a lot more strongly, and so it falls faster and it hits harder. Okay, now let's do the quick check. And then we'll move on to the independent practice and the homework. Infer. Mars is a planet that is smaller than Earth. How would the pull of gravity be different on Mars, and why? Well, gravity on Mars would be less than on Earth because Mars has less mass, so it's smaller. The pull of gravity is not as strong as it is on Earth. The critical thinking question. The sun is much more massive than Earth. Do we feel the pull of the sun's gravity? Explain. Think about that. Really think about that. Okay, gravity also depends on distance. So the distance, how far apart things are, also affects gravity. Although the sun has a significant gravitational force because it is huge, so that means things that are right there are pulled very strongly to it. It's too far away to show a noticeable effect. So we don't feel it pulling us toward it, but the orbit of the planets is an example of the sun's gravitational force. It is keeping all of these planets in orbit around it, just like the moon is in orbit around the Earth because of our gravity. Okay, so what you should do now is you should go ahead and get out today's packet for Friday, April 20th. And you're moving past the the Phantom Tollbooth homework because we're a day behind, so you're not actually doing that today. You'll do that on Monday. But yes, you have this independent practice. It's questions based on that picture of the speed skaters. Now, remember to answer these questions. Try to answer them in complete sentences. Sometimes you can answer them based on the picture. There is a better version on page 486. And some of them you have to come up with the answers on your own. Now that the information might be near that picture, or it may be something that you have to think about what you read and what you see and what you already know and put those together to come up with an answer. Then on the back, you're going to answer some questions about gravity using that diagram on page 488. Remember, please write in complete sentences because there's plenty of room to write in complete sentences. Some of the answers will be based just on the picture. Some of them you'll have to look back in the book. Okay, so go ahead and do those 2 pages that 1 page, both sides right now. Do the independent practice right now. The how do forces change motion and what is gravity. And then right after or later on today, you can go ahead and do the chapter 11, lesson 1 outline. Remember, there is a critical thinking question at the end. Be sure to fully answer that question. Now, they give you a lot of lines because you need a lot of room. Remember to always explain your answer and write in complete sentences and watch your grammar. Okay, go ahead and get started on the independent practice, and then you can do the homework now or you can do it later.